So the people who didn't come will have access to what I go over today. So the exam 2 to come on Thursday. Make sure everyone arrange a time for it. It will be 2 hours long. And the exam will cover all the chapters after exam 1 from chapter 3. Normal distribution. I'm gonna list the topic here. Let me share my window with you. Right. So we're gonna have chapter 3, normal distribution. I'm gonna try to make the font size bigger. Right. And then chapter 11, distribution of sampling distribution. And that's central limit theorem. And then we go to chapter 14. This is starting to work on inferences. And this is the first inference we learned. It will be one sample Z confidence interval. And then chapter 15 will be this one sample Z hypothesis test. And then chapter 18, this will be one sample T problems. Basically, you're going to have one sample T confidence interval and one sample T test. And then lastly, chapter 19. So we're going to deal with 2 sample T problems. And here we're only going to focus on the hypothesis test. So we're going to do dependent sample. That will give us a paired t-test. And then we're going to also have independent samples. And that will tell us to do the pooled variance t-test. There's another procedure that's also independent samples. That's Welch's t-test, but we don't require that. So we're only going to focus on pooled variance t-test for the independent case. All right. So make sure you go over all of the chapters and go over the homework quizzes. All the questions will be similar, just like what you see, in exam 1. You're going to see similar questions in the exam from the homework. And the exam has multiple choice part and open-ended questions, just like the exam 1 as well. For multiple choice questions, it's still going to be like 45 points, and then the rest will be open-ended questions. So for open-ended questions, I require you guys to write detailed steps. So basically, I read by procedures, not the answer, right? So make sure you show me the reasoning of how you do that, why you do that, so I can follow your thoughts and to grade your work. And also that's benefiting you as well. So basically, if you are on the right track and it did everything, to the procedure they're supposed to use, but you end up getting a bad answer, you're not going to lose much points. I'm going to give you partial credits for all the correct procedure provided, right? So try to give detailed procedure. When I say detailed procedure, it doesn't mean the math calculation, right? I don't require math calculation. You just need to show me how and why, right? So for example, if you want to calculate something, I want you to write a formula down. At least you plug in the numbers as into the formula form so you can see why you got that number, instead of just saying, hey, this is that number, but have no idea where you get it. And if you get that number wrong, you're going to lose all the points because you don't have the process for it. All right. So then let's go over these, each of the topic very quick. And this will be very, very brief. If anyone have any questions in the meeting, just stop me anytime if you want me to go, over something in more detail, okay? So let's talk about normal distribution now first. So normal distribution is a continuous distribution. So compared to binomial is discrete distribution. So normal is continuous. So continuous distribution we learned in chapter 10, we need to use a special tool to describe that distribution. That's called a density curve. Right? So how do I draw a density curve of normal distribution? That's pretty easy. So basically, a lot of people already seen the look of this shape, right? This is a typical normal distribution density curve. So the center of the density curve will be the value of mu, and then the amount of the spread will indicate how big your standard deviation sigma will be, right? So for any normal distribution, it's going to have two parameters. Parameter mu, that's population mean, and then parameter sigma, and this population standard deviation. So for example, you can say a variable x has a normal distribution with mean of 100 and a standard deviation of 15, right? Okay, so the first number in the parentheses always indicate that's the value for mu, and the second number always indicate the value sigma. Just get used to the format, the notation, and you're encouraged to use those notation as well. It's a lot easier than writing a long sentence to state a variable x is normal, right? So then we just talked about mu is the center, sigma is the amount of spread. If you have two normal density curve, side to side, then you should be able to tell which one has larger mean, which one has larger standard deviation. So you have A, you have B, right? Now when you look at this would be mu of B, and this will be mu of A on x-axis, right? Whatever that value is on the x-axis, that will be the population mean. So clearly B has a larger mean. It's because more to the right. And then standard deviation, B is larger than A because this amount of the spread for B is bigger, right? So I can tell that. Okay. So that's density curve. So density curve make things a lot easier, right? So in density curve, there's one feature we learned in chapter 10, right? So anytime if you want to find probability from a density curve, the probability will be indicated by the areas, right? So I always use area in the density curve to represent probability. So then in chapter 10, we have a regular shape density curve, like a rectangular shape, right? If you want to find area of any specific event, it's easy. Base times height, rectangular shape, right? But when you have a normal distribution, if you want to find area of any part of the curved density curve, then you don't have that luxury, right? You don't have that formula to calculate the area anymore. So we need to use some external help. We need to use some other tool to quickly find the area or probability of a normal distribution. So then how do we find, probability from normal distribution? We have two different ways. One is we use the empirical rule. So we have 68, 95, and 99.7 rule. So this rule is very simple. You only need to remember three numbers, 68, 95, and 99.7. And what it says is, you have a normal distribution with mu and sigma as parameters, then if you measure one standard deviation from the center mu on both sides of the normal density curve, then the middle probability enclosed will be 68%. So the middle area will be 68%. That's by the rule. And likewise, if you measure two standard deviation from the center, the middle probability will be 95% enclosed, right? And then three standard deviation from the center, that's 99.7%, right? So then this is the empirical rule. You only need to remember 3 numbers. 68 is for 1 standard deviation. 95 is for 2 standard deviation. 99.7 is for 3 standard deviation. And it's always measured from the center mu on both sides, right? And then you, of course, you need to understand for any distribution, the total probability is 100%, right? That's from chapter 10 as well. The probability of any sample space need to be equal to 1, right? So that's about density curve and probability, and that's about it. And then the density curve, if you use empirical rule, you can only find probability of normal event if the event is bounded exactly by the 7 marks. So from mu plus 1 sigma plus 2 sigma plus 3 sigma minus 1 sigma minus 2 sigma minus 3 sigma. You have 7 marks, right? If you want to find the probability of any event that's bounded by the 7 marks, that's fine. You can use the rule. But if you want to find a probability that's not bounded by the 7 marks, then you have a problem. This rule doesn't work anymore, right? So we need to use a different approach to find the probability of Z normal distribution. And that's how we introduce a special distribution as Z distribution. Okay, so Z is basically a special normal distribution. It's normal 0, 1. Okay, so population mean will equal to 0, population standard deviation equal to 1. So then for this special distribution, we make a table for it. We make a table to indicate the probability of any single value on the Z-axis with the corresponding probability to the left tail. And that's what our Z table is. Right? So make sure you know how to use Z table then. Z table, if you look at the design, you have Z-score on the first column and as well as top row. So combining first column, top row, that will give you a Z-score. And then everything inside the table, the 4 decimal place values are probabilities, right? So you have 1-to-1 match between a Z-score and a probability. For example, if you look at Z-score 1.12, you're gonna look at 1.1 here, and then find 0.02 here. So combining that will be 1.12, right? Then the corresponding matching probability will be the cross section of those Z-score, right? So then 1.12 will match with a probability of 0.8686. So 1.12 will match with 0.8686. Okay. Then what does it mean? We need to understand what it means. There's a relationship between them, right? But what is that relationship? So we need to go to the normal density curve on top. So basically what it tells us is if you have a Z-score 1.12 here, then the total area to the left, or the total probability to the left of 1.12 will be 0.8686. Right, so this is the key thing to read from Z table. So if you translate that into mathematical form, that'll be probability of the event is everything, all the Z-score that's to the left of 1.12, right? And that probability is corresponding to the area looked up, that's 0.8686, right? So you can only use Z table to look up probability if the sign is smaller than sign. When it's greater than sign or in between signs, you can convert it to be smaller than sign before you go to Z table. So that's very important. Always pay attention to the signs, okay? So that's about normal distribution. Then for any other normal distribution, for any distribution, normal distribution, so if you have X with a normal distribution with any parameter mu and any parameter sigma, there is a simple relationship between Z distribution and other normal distribution. You can always standardize X into Z by the formula Z equal to X minus mu divided by sigma. So then for any X event, applying this formula, you can always standardize that X into Z. And then you can look up the probability from Z table. And that's it. Okay. So that's about normal distribution. And then we talk about a special concept for binomial distribution approximation. So we use normal distribution to approximate binomial distribution. Okay. So binomial distribution probability is very hard to find because you have that long formula, and the formula is not too bad if you calculate one outcome at a time. But the problem is you have to calculate one at a time. If you want to calculate probability of X greater than 25, for example, but the sample space is from 1 to 100, you need to calculate many, many times. That's very, very time consuming. But normal distribution is different. For any event, you specify the event range. You can standardize that event into Z, and you can get the probability from Z table right away, one step, right? So normal is so much easier to find probability. So for some binomial distributions, we can approximate it using normal distribution. So we sacrifice a little bit of accuracy, but we can save tons of calculation effort, right? So that's what we do. So for any binomial distribution, with parameters n and p, right? If the conditions are met, we can do approximation using normal. Right? So then what are the conditions? There are two conditions. One is n times p is greater than 10. And the other is n times 1 minus p is greater than 10. So if you have a binomial distribution, n and p are provided, check if those two conditions are good. If they're good, then we can use normal approximation, right? Okay. Then how do we approximate? It's very simple. So basically, from binomial distribution, you can calculate mu and sigma. So mu will equal to n times p. And the sigma will be square root of np 1 minus p, right? So then if you have n and p, you can calculate mu and sigma. Then simply we say x is binomial, right? But x is approximately a normal distribution. And with whatever mu you calculated here and whatever sigma you calculated here as the two parameters. Then, for any event of the binomial distribution, for example, if you want to find probability of x greater than 24, you can just use a normal procedure you learned. You have a normal event with normal parameters. You standardize into Z and look up the probability from Z table. One step, you got the probability done. Instead of using binomial, you probably need to calculate like 20 times, right? Okay. But here, when you use normal distribution to approximate binomial, we need to pay attention to a special term called a continuity correction factor. Okay. So the continuity correction factor is very simple. Binomial is discrete. So you have 24 here. the next value will be 25. You cannot take 24.1, 24.2. It's a count variable, right? It's distinct. It's discrete. So we need to compensate on that discrete feature when we use normal distribution. And since the counting is only plus, by 1, right? It's from 24 to 25 to 26, right? So we're going to take half of that 1 on either side. So we're going to either add or we're going to subtract 0.5 from the boundary that's given. So the rule is very simple. Think about if you have a binomial, if you have a binomial event. So if you're saying x is greater than 24, think about this event by itself. Okay, so we're gonna look at whether there's including this 24 or not. Okay, so if you don't include this value, doesn't matter if it's less than or greater than 24, but if you don't include that point, you don't have the equal sign. Then what happened to the probability? Compared to you have the equal sign, you're gonna have a smaller probability, right? You're missing a point, right? So then in this case, we're gonna either add or subtract 0.5. You will always add or subtract 0.5. But if you don't have an equal sign, you're gonna try to decrease the probability of the event. So we know probability in normal distribution is just area, right? And if you have equal sign, on the other hand, that will make your probability bigger. You include an additional point, right? So in this case, we're gonna either add or subtract 0.5, but now we're gonna try to increase the probability. And that's the same as area of the event, right? So this is a rule to decide when do we add 0.5, when do we subtract 0.5, okay? So for example, if you look at event prop x greater than 24. So if you treat it as a normal distribution, this is x, and 24 is here. So we need to add or subtract 0.5 to 24. You have to do one of them, but which way do I do? Since it doesn't have equal sign, we need to follow this rule right here, right? We need to try to decrease the area. So where is the area we're looking for? The sign is greater than sign, so we need to look to the right, right? Then what do we want to do with 24? It will be either become 24.5 or 23.5, right? So which one do I choose? If we want to have a smaller area, it will become 24.5, right? So you have a smaller amount of the area that's being enclosed because it doesn't have that equal sign. Right? So a lot of people get confused with this. You always need to look at which direction of the probability you're looking for. Then you decide, which way you do. But the key thing is, if you don't have equal sign, make the area smaller. If you have equal sign, make the area bigger, right? Okay. So that's about it in chapter 3, normal distribution, right? Make sure you understand everything and able to apply it appropriately, right? So now let's look at chapter 11. Chapter 11, there's not much to talk about. Chapter 11, basically, it just tells us why normal distribution is the most important distribution, because from central limit theorem, the sample mean, x bar, will follow a normal distribution, regardless what kind of distribution the population has. So for any kind of data, if you have a large enough sample, the sample mean x bar will always follow a normal distribution. A normal distribution has two parameters. And for the two parameters, we can get those parameters from the central limit theorem as well. So for first parameter, that's population mean, it will be the same as original population mean, right? So that will be just mu. And then for the second parameter, sigma, it will be changed from original population. So it will be sigma over square root of sample size n. Right? So compared to the original distribution, if the original distribution X has population mean, mu, and the population standard deviation sigma, then the sample mean of that population will have, a normal distribution with parameter mu and the sigma over square root of n. X doesn't have to be normal. X can be any distribution. As long as it has a mean and a standard deviation, then the sample mean X bar will always have a normal distribution. So that basically tells us why normal distribution is most important, because regardless what kind of data you're dealing with, doesn't matter what population distribution is, as long as you take a large enough sample, the sample mean will follow a normal distribution. So it makes normal distribution a universal tool to analyze any kind of data if you want to, do the inferences on population mean, right? Okay. So then this is it. Then the rest, you just need to pay attention to the wordings of the problem. So if you're being asked about a probability, is it asking about on a population distribution, or is it asked about a sampling distribution? So basically, is it asking for a probability related to X bar or individual X, right? So if you ask about a group of people, then that's X bar, right? This average of a group. Then you need to use central limit theorem to find a new normal distribution to solve the problem, right? If it's asking for individual X's from the population, then whatever that population distribution is, you can solve with that distribution. And most of the time in the class, we use normal distribution as well. But it could be binomial. It could be any other distributions. But the sample mean X bar always have a normal distribution. And that's from central limit theorem. The only condition is we need to have sample size n is large enough. Okay, so that's about it in central limit theorem. And in the questions, a lot of students got confused between the word total and average. So let me give you a example real quick. So I think in the quiz and homework, there's a question asking, so we're saying adult IQ score has a normal distribution with parameter mu equal to 100 and sigma equal to 15. So a question can ask you, what is the what proportion of adults have IQ higher than 110? This is the typical normal distribution problem, right? They're asking for individual adults. So basically, just like if you randomly choose one adult, how likely is that adult IQ score to be over 110, right? So you're looking for probability of X is greater than 110, right? So you standardize with mu and sigma, you find from Z table, and that's it. And I can ask you also, if 5 students, 5 adults are randomly selected, what is the probability that the average IQ of the 5 adults is higher than 110? So then this is asking for an event of X bar is greater than 110, right? So you have a sample of 5 adults. The average of the sample is your sample mean X bar. So in this case, you need to find a distribution of X bar, then standardize using normal distribution and then find from Z table, right? So the key thing is now you need to find distribution of X bar, right? The mean is the same as original, and standard deviation will be original divided by square root of n, right? So then you standardize. And then here is a lot of students will struggle. So if 5 adults are randomly selected, what is the probability that the total IQ of the 5 adults is higher than, for example, for 480? So a lot of people just struggle with this. Here, just need to use some common sense to convert the average into the total into average, and everything will be the same, right? So if the total score of the 5 adults is higher than 580, what will be the average of the 5 adults will be? So looking for probability of total greater than 480, then on average will be greater than 480 divided by 5, right? So it'll be 96, right? And then it will become the same question as the one above, right? So the total is converted to X bar very quickly, okay? So that's about it in chapter 11, central limit theorem, the distribution of sampling distribution, right? So after that, we're ready for inferences. So we learned all the theories we need. We can describe the data as we wanted, using graphics or calculating some measures like a mean, standard deviation, correlation, regression, right? But now we're gonna study inferences. So how are we gonna make conclusions about the population? Right? So inference is a procedure to draw conclusions about the population, right? So please make sure you understand what the inference is. Anytime when you do an inference procedure, your conclusion is always about the population, right? Don't conclude back to your sample. You don't need to do inferences on your sample, all right? Your inference is always on the population. You know exactly what's going on in the sample. You can calculate the sample mean, you can calculate sample standard deviation, you can calculate any statistic you wanted from the sample, but that's not your interest. Your interest is the population, right? Right, so inferences, we have 2 general type of inferences. One is confidence interval, and the other is hypothesis test. They have different purpose. So if you want to study the population, how are you going to study it? What do you want to know about it? So you have a population, for example, all MSU students is their population. But if you want to estimate something out, you want to see, hey, what is the average debt of all MSU students? You want to estimate something, right? So then you need to choose confidence interval. So there's a population parameter that you want to know about. Then you want to estimate it. That's confidence interval, right? But instead, if someone make a claim about the population, people make claims all the time, right? If someone's saying the average debt of MSU students is higher than $30,000, so there's a claim being stated, and you're evaluating that claim as being true or false. Or for example, someone may say, this new drug is more effective than old drug. There's a claim being made, right? And we want to evaluate if that claim being true or false. Then we need to use a hypothesis test. So we need to assess the claim being true or false. right? So make sure you understand the different purpose of doing common interval and hypothesis test. That will give you a good, judgment. What will be the appropriate procedure for the inference problem you're working on, and that will be as a knowledge as required for the course. So you learn different tools, all different kind of common intervals and hypothesis tests. They're just like a tool. They're, one is hammer, the other is plier. And then when you work on different projects, you need to use different tools, right? You need to have a good judgment. So you need to understand the relationship between them. And then, also the differences between them. So you can make a good judgment call, right? Okay. So we're gonna put all the inferences procedure together so you can see the differences and similarity between them, right? So common interval and hypothesis test, that's in general the two type of inferences we do, all right? And to be specific for the procedure of common interval, it's pretty simple. You have the formula provided either for a Z common interval for one sample or a T common interval for one sample. All you need to do is just calculate the values of the range, and that will be the range of estimation, right? So the population mean will have that much % of confidence to be within those two numbers, right? It's more likely to be in that range. That's how you estimate it. There's no procedure you need to follow as long as you write the formulas down, plug in the numbers correctly, and then write a meaningful conclusion. For all inferences, I require you to write a meaningful conclusion. All right, that's very important. Basically, the meaningful, it just means don't use statistical term. Use a common language that your boss, who has no idea what statistic is, has no idea about what population or sample is. So they can read their conclusion and understand what they're trying to tell them, right? So write a conclusion in common words, use the context words, so that everyone can understand what the point you're trying to make, right? So for a Z confidence interval and T confidence interval, if you look at a formula, I'm gonna copy the formula real quick. Will be just like this. So all you need to do is just follow the calculation, right? And then make sure you write a meaningful conclusion after, and that's it. Okay. So I'm gonna focus on hypothesis test because a lot of people I feel they struggle with hypothesis test. Hypothesis test, you need to follow exactly the 5-step procedure as indicated in the class, right? And you can't take any procedure off. Every step has a meaning in it. It's gonna help you to answer the question correctly as well. So you can refer back for the previous step, you have a good reasoning for the whole process, right? So the first step is stating hypothesis, right? So if you are trying to decide if a claim being true or false, you know that claim already in your mind, right? That claim is your hypothesis. In general, we have two different types of hypothesis. One is null hypothesis, the other is alternative hypothesis, right? The null hypothesis always claim something being the same. Right? So if that claim is stating something being the same, saying the average data of MSU students is the same as $30,000, or the new drug has the same effect as old drug, right? So that's a null hypothesis. And alternative hypothesis will be a claim stating something being different. Right? So if that claim is claiming something being different, for example, the average data of OMSU students is different, is not equal to $30,000, or is higher than $30,000, or is lower than $30,000, then that's stating something being different, right? So that's alternative hypothesis. In general, the null hypothesis, you're only gonna have an equal sign, right? Something being the same as something else, you only have equal sign. And for alternative hypothesis, it could have greater than sign or smaller than sign or simply not equal sign, right? So please make sure you're able to identify the hypothesis from any research scenario. What is claim being, being made? What claim you're trying to evaluate? Is it stating something being different, or something is higher, or something is lower, right? So the key thing is alternative hypothesis, because null hypothesis is always stating something being the same. There's no difference, right? Okay, so that's first step. Second step, state the rejection rule. Right, so make sure you use p-value in the rejection rule. That's what we cover in class. The p-value rejection rule is always stated as if p-value is less than a blank value, then reject the null. So basically tell you when you're able to reject the null, only if p-value is small. And smaller than what? Smaller than type 1 error rate, right? So type 1 error rate is alpha. So type 1 error rate is a user-defined value. So when you do a study, you need to define how much type 1 error you want to allow in a study. It's an error, so you want error to be small, but how small do you want it to be? You need to have a value in your mind, all right? So that's what alpha is, okay? So whatever alpha you decide will be put into the blank, and the default value will be 0.05 in a class, right? So if for any problem, if the type 1 error rate is not given to you, then use 0.05 as a default value, because 0.05 is most often used values, right? There's no good reason why, it's just habit. Okay, so in real data, project, you should really decide what type 1 error rate you should choose for your particular study. So you have two types of errors: type 1 error and the type 2 error. And the two type of error, just like the trial process. Let me open the PowerPoint files to refer to that. So type 1 error and the type 2 error, they are both errors, and you want to control them to be small, right? So let's think about the trial process. The defendant could be guilty or innocent, depending on if the defendant is committed a crime or not. So it could be innocent in nature, or it could be guilty in nature. That's translate to our null hypothesis and alternative hypothesis. Null hypothesis could be true as in nature. He stated a true statement, or it could be false, right? But we are going to make a decision about if it is true or false based on the sample we collected. It's just like in the trial process. The judge will make a decision based on the evidence being collected. The evidence, just like our sample. The sample is our evidence, right? But even when you have evidence, when you have some support, you still have a chance to make a bad decision. Maybe you have a false sample. Maybe your sample collected is bad. Maybe the evidence you collected is bad. Someone forced it, right? So in that case, you could make a bad decision, and all the bad decisions are an error, right? So for example, for the trial process, if the judge decided an innocent person is guilty, he's making a mistake, and that mistake is called the type 1 error. In our case, we'll be reject the null when null is actually true. You reject the true null, right? On the other hand, if the defendant is guilty and the judge couldn't convict him based on the evidence, then that's another error, but that's a different error than the first one, right? So we call this a type 2 error. So in our case, we'll be failed to reject null when null is actually false. So you fail to reject a false null, right? So type 1 and type 2, they're both errors. So in real projects, you need to control both error rate to be something that you prefer. Controlling type 1 error rate is very, very simple. So basically, for every hypothesis test, you define alpha value. Choose alpha. If you want the type 1 error rate to be small, choose 0.01, choose 0.001. or 0.00001, right? However small you want. So how are we going to choose that? It should depend on the consequence of that error. So for example, when you talk about the trial process, if type 1 error is referring to innocent people is being put in jail. Type 2 error is the guilty person is walking free on the street. So which error is more important, in your opinion, as a researcher? It's a hard decision, but you have to make one, right? If you think they're both important, that's fine. But, anyway, so if you think type 1 error is more of a concern, choose a small alpha. If you think type 2 error is more of a concern, one way to control small beta type 2 error is actually make alpha bigger, right? So you make alpha bigger, beta will be smaller. And the other way to control type 2 error is increase your sample size. Increase your sample size is always good for any kind of study, right? Like in confidence interval, when you increase sample size, the margin of error will drop, right? So your estimation interval will be small. That's more precise. And in hypothesis test, when you increase sample size, you can have more power. So you can have smaller type 2 error. And then earlier we talked about consequences. So for example, how we're going to choose a bigger alpha as 0.10 or 0.05 compared to smaller alpha like 0.01 or 0.001, it should depend on the consequence. So for example, if you're saying you're doing a study about a drug, right? You want to see if the drug will harm people's health. So the error, when it happens, you could lose people's life. People will be poisoned and die, right? So in that case, you want that error rate to be small because the consequence is too serious. You don't want the chance for that to happen is big. You want to control that chance. But if you want to do a parking study, you want to see if you have enough parking around a facility building. What's the consequence? The consequence, someone drive around and couldn't find a parking space and need to park like 5 minutes, 10 minutes away. But that's not as serious, right? So you can do 0.05 or you can do 0.10 even, right? So that's type 1 and type 2 error. Okay, so state rejection rule, always if p-value is less than alpha, then reject the null. Then step 3 is the calculation part. So you need to calculate, all the calculation occur here. So you need to calculate test statistic and find p-value, okay? So for all the hypothesis tests, there's always formula provided to calculate different test statistic and p-value. So for example, you have one sample t-test, one sample z-test, and 2 sample t-test for dependent sample and independent sample. All the formulas are provided, right? You can calculate test statistic. It could be either z or t, right? But for different hypothesis tests. Make sure you're able to calculate all those correctly. One thing you need to pay attention is some people get confused about where mu come from, right? So mu always come from your null hypothesis. You assume the null hypothesis is true for all the calculations and then find the probability for that, right? So the null hypothesis always state mu equal to something. So whatever that something is will be what you substitute into mu, right? Okay, and then based on the calculated statistic, you can find the probability from either a z table or t table. So make sure you're able to read tables. Some students can clearly see that they are not getting the probability from z table and t table. I will definitely take off points if that's the case, right? So make sure you learn how to use t-table and the z-table. That's part of the requirement of the course, okay? It's great that you can use softwares to get those probabilities, but that's not required, right? And that's not what I like you guys to do. You need to read off z-table and t-table. That's the most common table you use, even though you don't use it much when you do practice, but when you use the table more, you have a better understanding why p-value is, that probability is this instead of that. So I don't want everyone to get value out of a black box. You know, you get a software, you plug in some kind of function in there, you get a value, but you have no idea what is it, right? So please try to use the table provided for the probabilities, right? And then step 4, basically, you're going to compare the p-value and alpha. Basically, just apply the rule here. So this is a rule to decide if you reject the null or not. If p is smaller than alpha, you find a p-value, and you already got alpha in step 2, compare them. If p is smaller, reject the null. If p is not smaller, then don't reject the null. So basically here, it just need to make a decision. Right? Is p smaller than alpha or not? And the last step, conclusion. Again, make sure you write a meaningful conclusion, right? So I need to write in a sentence to tell either your boss or whoever is reading your paper to understand what you're trying to tell after you analyze the data. Okay, so use some context words, common languages to tell what's the point you're trying to make after you do the analysis. So for all the hypothesis test, please make sure to follow the 5-step procedure. For any missing step, you will be deducted points, all right? And then there are differences of all the different inference procedure. For example, you have 2 confidence intervals. So when do you use which, right? So for Z confidence interval, you can only use it if the parameter sigma is given, right? So when you read off the project or the questions, is sigma provided or not in there? If sigma provided, you need to use a Z process. If sigma is not provided, then you need to use T process. If sigma is unknown, right? Then you also have 1 sample Z test and 1 sample T test. So when do I use which? Same condition, right? For a Z test, it's still a Z inference. If you want to use a Z inference, you need to make sure sigma is a known value. If sigma is unknown and you want to do a hypothesis test, it has to be a T test instead, right? And then we have 2 other procedures learned. One is deep pair t-test and pooled variance t-test. So when do I use which? They're both for 2 samples, right? So you need to look at if the 2 samples are dependent or independent. If they're dependent, you need to use pair t-test. If they're independent, you need to use pooled variance t-test, right? And that's about it. About the procedure, very simple. For confidence interval, do calculations, make a conclusion. Hypothesis test, doesn't matter which one it is, follow the same 5-step process. The only step being different is step 3. You're going to have different formulas for different hypothesis test procedure, right? So follow different formulas to calculate. But in the end, when you find p-value, the same, right? If you're doing a t-test, doesn't matter what t-test. After you get a t-statistic, you need to find a p-value from, t-table. If you're doing a z-test, get a p-value from z-table, right? And one thing I want to point out also, p-value is related to your alternative hypothesis, okay? For different alternative hypotheses, your p-value will take different forms. It's very easy to remember, but I'm not going to provide this on the test. You need to memorize this, all right? So if your alternative hypothesis is greater than sign, your p-value will have a greater than sign in the event here. Basically, it's going to be a right tail probability. If your alternative hypothesis is smaller than sign, then the probability will be the left tail probability. And then if alternative hypothesis is not equal sign, then p-value will be both sides. So if both sides, basically this probability adding this probability, right? So it's easy to just find one side, then we multiply by 2, and that's it. And Z distribution is very similar to T distribution. They're both symmetric, bell-shaped, center at 0. So when you have a T distribution, basically all the statistic here just become T instead. This is calculated, indicating that calculated statistic. And this will be calculated statistic. And this will be, T greater than calculated statistics absolute value, right? So there's nothing different. It's basically exactly the same form, right? Okay. So then that's about it for the exam 2. So basically you have normal distribution central limit theorem combined with a bunch of inferences, right? So make sure you're comfortable working with all the questions on the homework and quiz, and the practice exam is already available, I think, for quite a while. So go over these questions as well. And make sure you're prepared. And the concepts wise, it's a lot more complicated. It's a lot more difficult to understand. But calculation-wise, it's a lot easier. It's not as bad as when you calculate mean, standard deviation, correlation, and regression, right? But we do still require you guys to calculate mean standard deviation because they're going to be used all the time when you do inferences. All the formulas will have mean and standard deviation in it, right? Okay. So we don't do inferences on regression and correlation, but that will be an inference you can do as well, The regression equation we find is only applying to the sample, but is the population has the same regression slope and intercept. You calculate the regression in the sample, there's population regression is going to be somewhere around as well. What would be the population regression, right? So you can do those inferences as well, but they're more complicated and has more things involved. We don't want to go that far. So we only stop at the inferences and mean, okay? Any questions? Right. So that's going to be my review. I basically summarize everything very, very briefly. If you have any questions, you can ask right now. Or if not, we can have a meeting tomorrow at the same time. You're more than welcome to bring any questions over and we can discuss the specific examples and any questions you have on the homework and quiz or anything related to statistics, even your own project you're doing with other classes. I'm more than happy to assist you on the statistical part. All right. So any questions? Then I'm gonna stop the recording right now.